Okay, welcome everybody. Welcome back to the MIT category seminar. Today it's the last seminar of the year. So at the end, maybe before question time, David will speak a little bit about how this will continue. For today, we have Evan Patterson from the Topos Institute, who's going to talk about wiring diagrams, or undirected wiring diagrams, and how to implement them in CatLab. I advise anybody who has questions to please raise their hands in Zoom or write in the chat, or use any of the channels we have for questions like YouTube or the Zulip thread. Hello, Evan, and please go on.
Thank you so much. So thanks for having me back at the seminar. So when I last spoke at this seminar about CatLab, that was in January. And at that time, although quite a bit of work had already gone into it, CatLab still had the status essentially of a graduate student's side project. So since then, I graduated, and I've been fortunate to have the opportunity to work on CatLab and related projects close to full time. And so that's allowed the pace of development to really pick up, and my collaborators and I have done a lot of cool things, we think. And so that's what we are going to tell you, is what I'm going to tell you about today. This talk has several different themes, but they're sort of unified by the perspective of what you might call undirected computing. So using the apparatus of undirected wiring diagrams as a syntax and considering various algebras of that. And so this encompasses computing with relations, so relational computing, but then it also encompasses things that are dual to that, like gluing together of systems, and that can be seen as a kind of co-relational computing. Okay, so before I continue, I'd like to acknowledge the other people who have contributed to CatLab and other projects under the Algebraic Julia umbrella. So namely Andrew Boss, James Fairbanks, and Micah Halter, who are all at the Georgia Tech Research Institute, Sophie Libkind, who's at Stanford, and Owen Lynch, who is at Utrecht. I'd also like to acknowledge that for the past 6 months, my work has been funded by David Spivak at MIT via a grant that he received from the Air Force Office of Scientific Research. So I'm grateful to them for their support. Okay, so to frame this, I'd like to start by contrasting some different notions of composition, right? So applied category theory is often said to be all about compositionality, so why not start here? And a functional form of composition based on connecting things with inputs and outputs dominates not only in mathematics itself, but also in a large part of computing, particularly in most programming languages are based on a model of composing functions. But lots of systems that occur naturally, both in the physical world and in computation, compose in a more undirected way. So as I said at the beginning, that can manifest in different ways. They might compose as relations, right? So systems of equations or inequalities compose this way. Or as a sort of souped up version of relations, they could compose as spans, like tables and relational databases. And dually, they can compose as correlations, or more usually as cospans, and this encompasses various models of open systems. So another distinction, which is a bit more technical, but also important in practice, is the distinction between biased and unbiased notions of composition. So in most algebraic structures, both in classical abstract algebra and in category theory, the notion of composition that the structure embodies is decomposed into a set of primitive operations of fixed arity, like often binary operations. So for example, in a monodal category, you have sequential composition and monodal product, and you build up larger composites out of those. Whereas in an unbiased formulation, compositions are specified sort of all at once for any arity. So binary, ternary, quaternary, beyond. And the compositions tend to be themselves combinatorial objects of their own. And so these often have a graphical flavor via things like wiring diagrams. Okay, and so And as it happens, applied category theory offers mathematical tools to analyze all four combinations of these styles of composition. And CatLab itself is not particularly ideological on such things. It has functionality that runs the gamut across this space. But in this talk, we're going to focus on the bottom right corner of this square. And so we'll be talking about undirected wiring diagrams and applications of those, because that has been a focus of a lot of the recent work that we've been doing in the past 6 months. Okay, so undirected wiring diagrams look like this. So, and for some reason I see that the columns of my slides have been shifted around by the browser, but sorry for that. So they have these large unfilled circles, which we call boxes, and there's also these small circles that are junctions. And so each box has a set of ports, and the ports are connected to junctions. And moreover, there's also a set of outer ports, which would traditionally be drawn by an encompassing outer circle, but due to limitations of our graphics technology, we'll just draw these as these sort of dangling wires. And another thing to note is that ports are always connected to junctions, but when junctions have degree 2, we typically just omit them in the picture. So you can see that in some of those wires, but that is purely a drawing convention. Okay, so undirected wiring diagrams, or UWDs for short, are an unbiased syntax for undirected composition. So unlike the sort of textual syntax that you find in like most of math and also in programming, this is a combinatorial syntax. I mean, you draw it as a picture, but it is really a combinatorial structure. And as a result, it's embodied in code by a data structure for that. And mathematically, it's formalized as an operad. And the systems that compose according to this syntax give semantics for it. And so all sorts of different mathematical objects can be seen as the semantics of UWDs. So tensors, relations, correlations, so on. And as a result, these can have lots of different kinds of embodiments in code as various kinds of data structures. And the semantics of UWDs are formalized as algebras of the operad. Okay, so I'm going to give some examples of this to help make this a little more concrete. So one of the most obvious examples, in the sense that the notation of undirected wiring diagrams is already sort of widely used, would be tensor networks, where the boxes represent tensors. The ports of the boxes are indices of the tensors, and the junctions specify contractions or summations. And so this is a unbiased syntax for sort of generic contractions of tensors, which in the matrix case includes things like matrix vector multiply, matrix multiply, traces, Kronecker products, and so forth. So another example where this manifests are in conjunctive queries on relational databases. So I'll say more later about what that class of queries is, but there is some tradition in the databases literature of viewing these diagrammatically, but they're often drawn as these hypergraph pictures like you see on the left, where the vertices are basically things that you're going to join on, and the hyper edges are relations. And so I think it's clearer. So these pictures often kind of become spaghetti when you get complex queries. I think it's clearer to draw them as undirected wiring diagrams, where the boxes are represent data tables, which we'll formalize as spans. The ports are column names, and then the junctions are joins that are happening in that query. So another advantage of the UWD is that it distinguishes the ports from the junctions in a way that the hypergraph picture does not. Okay. So, and then a third example that we'll consider are what you might call open systems. And so there are different ways of formalizing this as directed cospans or structured cospans. But the idea is that these are systems which have a boundary through which they interact with other systems. And so one particular example of these would be open Petri nets. So on the left here, I've shown two open Petri nets as structured cospans and the way that they're in sort of a template for composing them. And then on the right, I've shown the undirected wiring diagram that corresponds to that pattern of composition. And so in this picture, the boxes are going to represent open systems. The ports are the interfaces of those systems. And then the junctions tell you where along those interfaces that you're going to glue in forming a composition. Okay, so that was the introduction. And so this is sort of an outline of what we're going to cover in more detail in the rest of the talk. So first, we're going to talk about undirected wiring diagrams themselves as a syntax. And so we're going to look at their operad structure. We're going to see how they can be seen as C-sets, and then we're going to see how this leads to their implementation in CatLab. Excuse me. In the second part of the talk, we're going to say a bit more about these three examples, which are all unified by being UWD algebras. And so we're going to talk about tensor networks, conjunctive queries, and unstructured cospans. Of these, we've probably done the least amount of work on tensor networks, and by far the most on structured cospans, and so that will partition that time accordingly. Okay, so so I should say first of all what an undirected wiring diagram is in a more precise way than the pictures, because the pictures are essential, but they're really are depictions of a combinatorial object, and this is what it is. So one way to say what an undirected wiring diagram is one within boxes is a cospan in a finite sets of the following form, where you have for every box a set of ports, you also have a set of outer ports, and then all of these are connected to a set of junctions by functions. Okay, so we can think of them as cospans of that form. Now, for reasons that will become clear later, we find it convenient to rephrase the previous definition, which is perhaps the standard one, in a very slightly different way, where we'll say that we're actually going to put all the ports of boxes together in one set P, and then to remember which box they're associated with, we'll add another set, an explicit set of boxes, and then a function that points from the ports to the boxes. And so if you think about it, this is encoding the same data as in the previous definition. Okay, and so this is how the data is stored in CatLab. So first of all, to specify this combinatorial data directly would be rather tedious, and so we provide some utilities to make it easier to input an undirected wiring diagram. And so one of those is this relation macro, where you basically can write down the diagram in sort of a relational syntax. Okay, so here this is a very simple diagram with two boxes that corresponds to just composition in sequence. And we can see how this is represented as a set of tables which contain the information in the previous diagram. So for example, there are two boxes, each with 2 ports, and so there's a total of 4 ports. We can see that in this table here labeled port. And so the first 2 ports have a box which is 1, and the second 2 ports have a box which is 2, and so you can see how this jives together. Okay, so that's the underlying representation, and we'll say later kind of how that is part of a larger system. Okay, so now let's talk about the the operad structure of undirected wiring diagrams. So informally, this is a kind of hierarchical composition or substitution. So in which one or more boxes are in a diagram are replaced with a whole nother diagram. So for example, we'll start with this diagram shown here, and then we're going to substitute for the box labeled R1 this other diagram here. And these numbers, I've explicitly labeled both the ports of the boxes and the outer ports so that you can see which things are going to get glued to where. So the outer ports labeled 1, 2, 3 on this diagram are going to end up going to 1, 2, 3 of R1. And so when you do this O-compose is what it's called in CatLab for operatic composition, at position 1, you get the result of substituting this diagram in for R1. Okay. Okay, and so there's a lot on this slide, but this is just to say that, so that's the picture. The one way you can formalize what this is as a push out. So basically you set up a certain diagram, and then you take a push out of the set of junctions. And I mention this because this is actually how it's implemented in CatLab using sort of general machinery that we have for computing with finite sets and functions. Okay, so the point of the second definition that we showed is that it enables undirected wiring diagrams to be implemented as C-sets. And so we're going to take a bit of a digression from the main theme here to see how this works, because it's useful for lots of things besides UWDs as well. So remember that given a small category C, a C-set is just a set valued functor out of that category. And sometimes it's often called a co-presheaf, but I like to say C-set because it's a little shorter. And in CatLab, C-sets essentially serve as in-memory relational databases. So there's a generic data structure for them. And so in this scheme, finite sets are identified with just numbers and sequence. So in effect, we're working with the skeleton of the category of finite sets. And in that case, functions can be stored very simply too, as just arrays of integers. And in order to enable fast traversals, like if you wanted to walk an undirected wiring diagram by following its boxes and junctions, in order to do that efficiently, you need to be able to know like what ports belong to a box or what ports are incident to a junction. And so for that, we store inverse images or pre-images, or in database jargon, these are indexes on the columns, which allow for these fast traversals. Okay, so the simplest example of a C-set, which is nevertheless very useful, is graphs. So the schema for graphs is the category generated by two parallel arrows representing the source and target vertices of an edge. And so in that case, a C-set is just a graph, or a graph in the category theorist sense. Graph theorists might call these directed multigraphs. And so CatLab makes it very simple to define such data structures in a declarative way. So here we're presenting the schema for graphs as a finitely presented category, and then we're saying instantiate a type in Julia called graph for this schema and index the source and target morphisms. And then boom, you have a performant data structure for graphs. And so using this scheme, CatLab provides a graphs model that includes all sorts of graphs, both familiar and possibly unfamiliar. So the basic types of graphs that category theorists know and love, such as graphs, symmetric graphs, and reflexive graphs, variant of graphs based on half edges, various notions of graphs that are embedded in a surface, such as combinatorial maps. There's data structures for bipartite graphs, and so on and so on. And so, and moreover, you can sort of extend these with data attributes if you want, via a device we call attributed C sets. Okay, and so the point I want to make about this is that attributed C sets are an essentially costless abstraction. So they're a useful abstraction in that it includes both graphs and data frames as special cases. And usually if you want to make a new data structure, you have to code it up from scratch. Whereas here you can specify it in a declarative way. And moreover, because it belongs to the categorical world of functor categories, you get all sorts of generic tools available for you immediately, such as limits and co-limits, and we're in the process of implementing aspects of functorial data migration. Okay, but due to features of the Julia programming language, we can make this abstraction nearly costless, right? Because we can actually encode the schema completely inside a Julia type, and then generate specialized code for that type via metaprogramming, specifically through a device in Julia called generated functions, such that like the methods that get generated for the graph type are as if you had written a custom data structure for graphs. And preliminary benchmarks do validate that this yields performance comparable to packages that provide specialized data types, say for graphs. Okay, but so we're getting back to the theme of UWDs. So here's our schema for UWDs, which we saw before. And so now we can express this in code in the following way. So we define objects for the box, the port, the outer port, and the junction, and then we define the three morphisms in the diagram. So this is a direct translation into code of that picture. And then we can instantiate a type for that. And so this is exactly how the data structure for UWDs are implemented in CatLab. This is a copy paste. Okay, so now let's start to dig into some of the examples. So the first thing to notice about tensor networks is that at a syntactic level, undirected wiring diagrams are essentially the same data as you get from a tensor contraction as specified in the like Einstein style tensor notation, where you have indexes and then the summations are implicit. And so, and indeed in CatLab, you can translate back and forth between UWDs and this tensor notion, which really makes it very clear that there is essentially a direct correspondence between these things. So, and that's what's shown here. So parsing an undirected wiring diagram from this expression, and then also go in the other direction, generating code. And so besides its conceptual advantage, I mean, this also has the advantage of allowing interoperation with lots of tensor computing packages in the Julia ecosystem, because many of them know how to understand this Einstein style notation. Okay. And so the notation already sort of gives away the game in terms of what the UWD algebra structure is. It's, well, you just do the contraction which is specified by that summation notation. And so for any rig, so if we can think for now just the real numbers or the complex numbers, the tensors over that are an algebra of UWDs that are typed by natural numbers, the natural number identifying like the dimensionality of the Porter junction. And so there is a formula for like this operation, but it's not so perspicuous to write it down. But what I do want to point out an important aspect of this though. So it's true that you can write down this formula for sort of any arity, but the number of arithmetic operations involved is proportional to the product of the dimensionalities of the junctions in the picture. So for example, if you have a ternary matrix multiply, by which I mean an undirected wiring diagram with 3 boxes connected in sequence, then that has quartic time. But if you were to decompose that into like a binary matrix multiply followed by another binary matrix multiply, each of those have cubic time with the standard way of multiplying matrices, and so you end up with overall cost of cubic time. And so this gives an important lesson which applies more generally, although not perhaps universally, which is that for many algebras, it is important to do what's called scheduling or to decompose the diagram in order to do efficient computation. So that's a point we're going to return to later. But I want to first point out the way in which tensors become connected to relations, because this will seg nicely to our next topic. Okay, so if you take tensors over the Boolean rig, so the rig with 2 values, true and false, and you define addition to be or and product to be and, as shown in this Julia code here, then like a matrix over the Boolean rig is then a binary relation, and then a tensor over it would be a relation of arbitrary arity. And so early on in the development of the Julia programming language, the Julia developers actually wrote a paper where they pointed out that like Julia allows for efficient computation over semi-rings because its compiler actually generates efficient code, even though there's this struct here that's wrapping the Boolean value. So this is kind of neat. One of the advantages of working on Julia is that you can take generic tensor code and plug in this and get the ability to compute with certain kinds of relations. And then tensor contraction implements composition of relations. So one possible application of this, which has been introduced by Spivak and his collaborators, are pixel arrays, which are a fully discretized approach to numerically solving systems of nonlinear equations that use this approach. Okay, but I'm going to get into some of our other topics here. So conjunctive queries are a very important class of queries that people study in the context of relational databases, such as SQL databases. So they're important in theory. A lot has been written about them. They're also a pretty useful class in practice. And from a logical viewpoint, they correspond to formulas in regular logic. So the fragment of first order logic with conjunction and existential quantification inequality. So for more on that, there's a paper, graphical regular logic, which explores this connection. Okay, so for an example, the following diagram, which I've specified here and shown as a picture, finds all the vertices in a graph that participate in a directed 3-cycle. And if you're familiar with SQL, this query would appear as shown on the right. So basically you need to look over triples of edges such that the source and targets of those edges are configured so as to give you a 3-cycle. And that's what this query says. Okay, so in relational algebra, it's conventional to regard tables as being relations, and a lot of the literature on database theory is written from this viewpoint, but it's not only more general, but also closer to the way databases are implemented to think of database tables as being spans. And that's how we're going to think of them for the purposes of this UWD algebra. So we're going to say that a table within columns is a multi-span set. So by a multi-span, I just mean it's like a span, but it can have more than 2 legs or less. And so then tables of this kind, or if we're being careful that their isomorphism classes, are an algebra of the operad of undirected wiring diagrams. And so how does that work? So the idea is that undirected wiring diagrams are conjunctive queries, and those are specifying joins. So specifically, this UWD algebra performs what in database jargon are called cross joins and inner joins, are both encompassed by this. So specifically, you take, so the way this works is that every undirected wiring diagram, such as this one here for 3 cycles, translates into a diagram, as in the sense, a diagram in the category set by replacing both the boxes and the junctions with objects or sets, and then the mapping from ports to junctions defines the arrows in this diagram. So it's probably easiest to see it by example. And then you compute, and then to perform the join, that is actually the same thing as just taking the at least mathematically, that's the same thing as taking the limit of this diagram. And so all the diagrams that arise in this way, you can think of as being basically like generalized pullbacks, because they always have two layers, and they kind of have the form of a pullback, but they're more general, because you can have multiple pullbacks going on, or pullbacks of more than 2 things, and so on. So joins are limits, but also limits, we can kind of turn this around and observe that, well, then limits are also kind of joins. And so specifically, any algorithm that you have for computing a join is an algorithm for computing a pullback of a finite set. And so, and that's great, because in the databases literature, people have spent a whole lot of time figuring out how to do this efficiently, because it's one of the core things that a database has to do. And so we started to implement some of these algorithms in CatLab with the idea that we're going to use to do conjunctive queries on C sets. So there's the nested loop join. So if you're a category theorist, you know that you can compute a pullback by composing a product with an equalizer. And if you unpack what that's doing, that turns out to be what's going on in the nested loop join, which is the simplest, it's the naive algorithm for computing a join. And then there's other joins that, there's other joins that, for example, use sorting to avoid having to loop through all possible pairs of elements, or that use inverse images for the same reason. And so this hash join based on inverse images will be especially convenient for C sets when the thing in question is indexed. Okay, so anyway, so we've implemented these, and then there's work in progress to turn this into a query system for C sets. And so the goal of this work, which I expect to have a preliminary version of done by the end of the year, is to have a useful data analysis tool that goes considerably beyond data frames, which are sort of like the most common abstraction that you see in like typical like data analysis packages. Okay, so one thing that already works today is the generation of SQL queries from undirected wiring diagrams. So Andrew Boss maintains a package called algebraic relations, which the point of the package is to provide an ACT-inspired approach to scientific workflow management. So an ability to specify a schema for like a set of experiments or something, and based on directed wiring diagrams, and then to store the data from that experiment in a relational database. And as part of this package, there's the functionality to specify queries on that data via UWDs, and then to execute the corresponding SQL queries. So if you want to learn more about that, there's a blog post that we have that you can read about it. And at the end, the slides will be made available so that you can click all these links later if you wish. Okay. So now I want to make a point about the structural similarity that there is between these two examples of tensor contractions and database joins. So like tensor contractions, if you want to perform database joins efficiently, you need to decompose it into low arity operations, such as binary operations, in order to get efficient execution. And so in fact, this perspective that category theory provides clarifies that the following two problems are almost exactly the same. So the problem of planning the efficient contraction of tensor networks that are sparse is nearly the same as the problem of query planning for conjunctive queries on relational databases. And so that's sort of a neat observation. And so then the next question is, can we actually take advantage of this insight to share algorithms between those fields that are implemented according to the common abstraction of scheduling UWDs, which involves some kind of hierarchical decomposition of them using the operatic structure. And so this is work in progress. So CatLab currently has data structures for schedules on UWDs and knows how to execute them. But the real work of sort of implementing sort of interesting scheduling algorithms and testing them out and stuff, that is work for the future. Okay, so now I'd like to get into our third example. So this is the one that we have, I think, most extensively developed. And so I'll give an introduction to it here. So, open systems can be modeled by a device called structured cospans, which were introduced by Baez and Corser, building on earlier work on decorated cospans by Brendan Fong. And so the data that you need in order to define a structured cospan is, first of all, you have some category X, which is supposed to model the system itself. And then there's another category A, which represents the boundary of that system. So usually the category A is somehow simpler than the category X because the boundary is just exposing part of the information that's in the system. And then there's a functor L from A to X, which intuitively speaking kind of says how the boundary fits into the system itself. Okay, and so then a structured cospan is a cospan of the following form, where you have an object X, which represents the system, and then these two legs which specify the boundary of the system, conventionally understood to be inputs and outputs, hence the notation. But this is not really a directed setup. So you can, for example, you can always swap the two legs with each other to get another cospan. Okay, and so CatLab has extensive support for structured cospans in various guises. So it has a generic interface for structured cospans, and then maybe more importantly, it has built-in support for what you might call open C sets. So these are structured cospans that arise from the case when the larger category X is the category of C sets for some C, or attributed C sets. And then the boundary is just VIN set. For example, below here, the case of open graphs, where X is the category of graphs, which, as we've seen, is a category of C sets. A is category of finite sets, and the functor L is the discrete graph functor, which given a set gives you the graph with no edges and whose underlying vertex set is that set. So in terms of the perspective of open systems, like, you know, the boundaries of these systems are just are effectively subsets of the vertices. And so CatLab lets you basically construct types for these that you can compose with one line of code, because it knows how to work with C sets. Okay, and then for these, in the case of structured cospans, we've implemented the structure of a hypergraph category, but more to the point for today's talk, structured multi-cospans, which we'll see in a moment, form a UWD algebra. Okay, so So a structured multi-cospan is kind of what you would expect. It's like a structured cospan, but it can have a number of legs different than 2. And so structured multi-cospans are an algebra of the operator of UWDs that are typed by objects of A. And so how does this algebra work? So here's the picture. And this picture should remind you of the picture that we saw for composing tables and relational databases, because it's dual to it. Okay, so for every undirected writing diagram typed by objects of A specifies is going to do in terms of the algebra, is going to specify a diagram in the category X over which we're going to take a co-limit. So it's the same picture here, both the boxes and the junctions become objects in this diagram, and then the morphisms come from the port to junction map, and so this picture, apart from the presence of the L's here, which you need in the structured cospan world, is dual to the one for databases. And it's implemented in CatLab via CatLab support for taking finite colimits of arbitrary shape over attributed C-sets. So to implement, I don't show the code, but the implementation is really quite simple. You take the undirected writing diagram, you translate it into a diagram, a diagram of C-sets, and then you fire off the colimit. Okay, and so an application of this that we've been exploring is epidemiological modeling. So Michael Halter and James Fairbanks have done a lot of work on this. So in particular, there's the companion package called Algebraic Petri, which is maintained by Micah. And it uses open Petri nets to do compositional epidemiological modeling. So in fact, it's based on the whole grain Petri nets of Hakim Kok, which are, and this is convenient from our point of view because those are actually C-sets, although their morphisms are a bit more complicated than is, the morphisms aren't just natural transformations, they're some extra structure. So in any event, for the purpose, this relates to the present talk because we use the UWD algebra structure that I just described in order to do hierarchical model specification and construction. Okay, so an outline, the pipeline, the modeling pipeline is this. You start by defining some primitive open Petri nets that are going to be the building blocks of your model. So it might be an SIR model or an SIER model. And then you compose your larger model out of these using the UWD algebra. So for example, you might glue together models for single populations into a model with multiple interacting populations. Then you generate, so that gives you a Petri net. You translate the Petri net into ODEs, and then you solve the ODEs using existing machinery in the Julia ecosystem. And so for more about this, we have actually a series of blog posts about it that you can read. But I'm just going to show some pictures to give you a flavor, and if you want more information, you can read there. Okay, so here, so part of what Micah James did is to reproduce part of the coexist model of COVID-19 that was developed for the United Kingdom. And so here is this is as we'll see, this is a complex model. It's going to be built up hierarchically in steps. So this is the highest level composite that exists in the construction of one version of this model. So what you have here, so coexist 1, 2, and 3 are self-contained transmission infection models for for 3 different populations, and then each of those are going to interact with the others through cross-exposure processes. And so that's one of the one of the compositions involved. But the upshot is, at the end of the day, you end up with an enormous Petri net, and so that you would almost certainly not want to construct by hand. And so complex models like this illustrate the importance of a compositional approach to modeling, and UWDs and their algebras provide a particularly sort of ergonomic way of doing that. Okay, so to summarize, for me, I think UWDs and C-sets, which are both things that we've discussed in this talk, are interesting and hopefully useful, but they're also, I think, case studies that are supposed to support a broader set of theses, namely that category theory is notoriously general, but that generality can actually be translated into effective software abstractions for computing for science and engineering. And moreover, by exploring features of the Julia programming language, these abstractions don't have to result in severely degraded performance, while at the same time enhancing the speed at which new models and techniques can be developed, because you're pushing more things into a declarative rather than an imperative or mode of coding. Okay, and so in future work, we hope to continue to develop these themes with a focus on scientific and statistical modeling. So to conclude, I'll point you to some additional resources if you'd like to learn more. So for an introduction to the mathematics of hypergraph categories and a bit about operads and wiring diagrams, Chapter 6 of Fong and Spivak's 7 sketches is a good place to start. And we have more introductory references listed at our website. To get started with some of the programming aspects of this, for Julia itself, the Julia Lang website has a large list of resources, and the official manual is also pretty good. As for CatLab, we are working on documentation of various kinds. For now, the best sort of introductory content would be the blog post that we've written. So CatLab, as are the other projects in Algebraic Julia, are open source projects with liberal licenses. So we hope that people in the community will use them and possibly also help us develop them. So if you're interested in that, there are a number of ways that you could become involved with the project if you like. So in the first instance, if you have an application in mind, you can try to use these tools as a user and give us feedback on whether they work well or how they work or what the pain points are. So we also need to write more forms of expository documentation. So if you'd like to write, we would welcome that. And of course, you could also get involved as a developer, either on CatLab itself, developing sort of the core infrastructure, or in other packages, part of the ecosystem that we're exploring for various applications. Okay, so if you want to talk to us more about this, you can find us at the Julia Zulip. We have a CatLab channel there. A number of us are also on the category theory Zulip. You can ping us there, and of course, there's GitHub as well for issues and pull requests. So that's it. Thanks so much, everyone, for listening. And it was a real honor to be the last talk in the series for the year.
Thank you. Thanks a lot, Evan. Thank you for a nice talk. And so before we go to question, David may want to say a few words. Please go ahead.
Great, thanks, Paolo. Yeah, as Paolo and Evan mentioned, this is the last talk in the MIT category seminar. And so starting next year, we'll be working full-time at, Brendan and I and Evan will be working full-time at Topos Institute. It'll be based in Berkeley, California, but we'll have a presence on the web as usual. And So we will start a seminar there. I'm not sure if it'll start in January, but it'll start soon in the new year. And if you're on the current mailing list, we will send you, we'll use that to get in touch with you. If you're not, please send me an email at, I'll put it in the chat, but david@topos.institute. So, okay. And so I guess we should take questions for Evan, if anyone has any.
So yeah, there was a little bit of discussion about Michael Johnson's work. It's too bad that we are in an inconvenient time for Australia, so he cannot connect right now. But so maybe somebody wants to say something. You can raise your hands or write in the chat. Valeria has a question. Please,
Hey,
Valeria.
Evan.
Hi, Valeria.
Paulo. Yeah, do you mind going back to slide 24?
Yeah.
I mean, it's a question that I could ask you several other times, but I thought I wanted to.
Valeria,
I
we had a Valeria. There's a glitch in the connection, so if you can please repeat and a bit slowly because the connection is not great. Thank you.
Sure. The question is about why. I mean, you have tried to make this point before, and I'm just being a bit dense here. But why is the Julia language a better language to implement things like relations and tensors? You know, I know you have tried to make the point, but do you mind repeating?
Yeah, I can elaborate on that a little bit. So often what would happen is, like, if you had a data structure for like multi-dimensional arrays that you could put any kind of object in, if you put in an object that wasn't a primitive object in the language, like it was some kind of struct that wrapped another thing, like wrapped this Boolean value, then when the language does, if the computation is just being done in sort of an interpreted way, you may end up with having to box it, what's called like boxing and unboxing this value a lot, where every time you see one of these structs, you have to pull out this value, you got to do something, and you got to put them back in and make a new thing. And so that is like very inefficient. So Julia, although it's interactive, it's based on a just-in-time compiler. So when it sees this code with say like this tight Boolean rig for the first time, if it has some generic tensor code, when you first run it with this new type, it's going to generate specialized low-level code specifically for this Boolean rig type, which is able to basically avoid extra allocations associated with this. So you get the benefits of generic computing. Like I can define a new type with my own addition and multiplication, but I don't have to pay for that in terms of performance because the compiler can sort of compile that away. So Julia is not the only possible system with this capability, but like this would not, in order to make this work, say like yeah, so I'll leave it at that. Does that help? You're muted, I think, Lyra.
Yes, now I can unmute. Yes, that is very, very helpful. So if I get it, it is efficiency coming through just-in-time computing, JIT compilers. Is that the main thing that we're talking about?
That's a big part of it. Yeah. I mean, so Julia has the appearance of, Julia is essentially a compiled language which has the appearance of being interactive, but it's not. It's fully compiled. So, yeah.
That's great. Thank you very much. That was a brilliant talk. Kind of.
Thank you very much.
Thank you.
Okay. Does anybody else have any questions or comments or anything?
Well, I have a question. I don't know if it's very interesting, but like it sounds like with the databases, you implement not only a functor from C to set, but also a functor from C op to set op, basically. Like the indexes, you think of as you basically op that functor.
Right.
and then now you have a functor from C to set, and then sometimes you have functor from C, which really, I mean, C up to set up. And then it seems like you take limits in both cases, because you take limits for databases, but you take co-limits of sets for the like PetriNet stuff, which is like limits and set up. And I was kind of wondering if like the whole thing, I don't know if more abstraction is needed or useful in any way, but like, would there be any benefit in kind of like having an arbitrary target category set or set up or something else that you could just say?
So I didn't really get into it, but okay. So let me make sure I understand the question first. So like, you mean like having like C sets where the target category is not necessarily like a generic system for pre-sheaves or co-pre-sheaves where the
yeah, with target in a limit category rather than.
Yeah, I mean, I think that's certainly a good direction to explore, and like, because there are interesting cases where like if you replace set with other things like the category of posets or the category of metric spaces, you can get interesting structures that are sort of like C sets enriched with extra information. And so yeah, I think that's sort of a nice thing you get from the functorial semantics viewpoint. And so it would be, I think, neat to exploit that by allowing more flexibility there. So that'd be a good thing, I think, for future work.
I guess maybe the question was, is Julia set up to allow that level of like to allow you to replace that target category set by something more general, or would that be kind of above the?
Well,
like, yeah.
So it depends how you. I mean, so like one thing that Julia has, which you can always use, are like this notion of like generic functions that can dispatch on different types. So you could have multiple versions of like multiple kinds of CSIT implementations that all sort of satisfy the same abstract type and that have the same interface. Of course, lots of programming languages have sort of similar capabilities. Now it should be said that like the way CSITs are currently implemented is with like the storage of the data in the thing is pretty closely based on like the way you would represent a finite set on a computer. So like, it's sort of like optimized for that. So like if you wanted to do something like totally different, like if you wanted to have like continuous functions or something that were represented by equations, or I don't know, right? Like then you need to do something like quite a bit different than what we're doing. And I don't see really a way around that. So yeah.
Gotcha. Cool. Thanks.
So on Zulip, Eric Forges has a partial answer to Valeria de Paiva, again regarding why Julia. So maybe other people in the audience may be interested. So he said, another thing to add is that Julia is naturally compositional due to the multiple dispatch. So in addition to being able to define your own custom types, which other languages can do too, it also allows you to work naturally with the rest of the Julia ecosystem. For example, Evan and the CatLab group can easily plug into the differential equations ecosystems and the plotting ecosystem. Julia makes it simple to extend other packages without needing to access the internals of the packages. I guess that could be relevant too. All right, does anybody else have any questions or comments? Okay, since we don't have any more online discussions, so we're shortly moving to offline. Let me just say, since this is also my last seminar, so I'm very, very grateful for all this seminar. Thanks to all the speakers and all the audience. And thank you on my side too, because I've learned a lot of category theory this way. Thanks a lot.
Thanks a lot, Paolo.
And well, thank you, Evan, for a nice talk.
Yeah, thanks, Paolo, for all your work making this seminar series run this last year. So yeah, thanks to everyone.
Yeah, thanks to everyone. Thanks you all for coming.